mic check. Apparently, we have a
Yeah, it's
mic check.
working.
Thank you. All right, welcome back to day 2 of the Cosmic Capstone Challenge final showcase. We have a lighter day today. There are 5 teams presenting, including 3 out here in El Segundo. And then tomorrow we cap it off with 9 more, with I think 6 of them on site at Goddard. So that's going to be awesome too. Okay, ground rules. Okay, I was told I need to repeat this. If you're a visitor here in El Segundo, you cannot take pictures with your camera. We have a photographer here who will take photos. If you want photos of your team somewhere, ask your escort or your host, and they can take a photo with their company camera and probably get it to you. But you just can't take pictures on our campus. Those are not my rules. Those are company rules. Okay. Ground rules for everyone is we're again going to have the presenters and only the judges coming off of mute. So if the judges have questions at the end of the 24 minutes, they're free to ask questions. If others have questions, post them in the Zoom chat, and we'll I will voice those for you. If you have questions or something's going on, you post in the Zoom chat. You can reach out to myself or Joey if there's something that's not urgent. And yeah, if you're attending in person, obviously we have a smaller crowd here today. I think we're gonna have probably end up with 3 teams. Right now there's 2, but be respectful during the presentations. Click, 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 click. I don't know if that was me. Okay, housekeeping. I think you guys were all here yesterday. You can see where the emergency exits are. Restrooms are on the lobby level. You can use the restrooms, but otherwise you have to stay in this main part of the area here. Case of emergency, in case of an earthquake, if you're sitting under those hanging lights there and you get an earthquake alert, that is when you should duck and cover. I don't expect another earthquake today in Southern California, but if there is one, get under those tables.
I'm sure glad I'm in Colorado.
Well, it's funny because, I mean, if you're on yesterday, like the San Diego State students were here and their campus got rocked. It wasn't a huge earthquake, but it was big enough that probably knocked some books off the shelves. That's yesterday's schedule. Today, so we're opening them up with 2 teams from the University of Texas. The first team is Zenith Engineering Solutions from University of Texas at Arlington. And after them is the Miners from the University of Texas at El Paso. And this afternoon, we have a couple remote teams, and then Space Bender from right here, Cal State Los Angeles. Tomorrow, you can see we have 9 more teams, so it's a packed day. They have, if you're there, there's tours in the morning. You would have gotten emails from NASA about those tours and the rest of the event. But you can see there's actually 6 teams presenting in person tomorrow. I think this one is out of date. I believe one of the later Penn State teams is also presenting in person. Okay. Cosmic background. We did this yesterday, so I'm going to do the abbreviated version. It's a consortium that's been established to bring together the community interested in space mobility and ISAM. Workforce development, that's the group Joey and I lead or facilitate. So far we've been mostly focused on C3, but also helping provide resources for people to learn more. We're looking at starting to develop this year an ISAM mini course, so kind of a self-paced curriculum so people can learn more about ISAM and call it I don't know, regimented way, but a more organized fashion. The C3, again, I think everyone's familiar by now. Design a payload to be hosted aboard the X-Class bus. Demonstrate 3 or more operations to provide an on-orbit autonomous ISAM capability. Every team has a mentor. This year, we've had 2 events, the Flash Talks in December, which I'm pretty sure will repeat, the Outbrief now. We may add one more. We may add one more requirement, which would probably just be, towards middle of November, which would just be like some sort of very simple literature review because we kind of imposed that last year along the way, and actually I think it was a good idea. So at some point during the year, we'll incorporate that. Um, these are the teams that have participated. Some of those were only single semester, so we have 23 for the full year. That was a Dodger game I went to on Sunday. We're gonna have prizes. We have judges. So far, we do have at least 5 judges for each team. From yesterday, I expect we'll end up with about 7 or 8 per team. Um, we're standardizing the scores to the best of our ability, and we'll tally them up and announce sometime before the end of next week. So while school's still in session, I don't want to promise we'll do it sooner because there's always something that comes up. We're going to send a survey out probably again early next week. We'll probably send a survey. We'll send the next year's info packet, and we'll send the announcement of the winners all in one email. And the really big questions: what would you change? What would you keep the same? We might ask one too. Was like, what was the most interesting thing you saw from other teams? Because I think like you guys now have eyes where you're watching these and you're learning from them and getting ideas and kind of like what we're looking for is themes. Like with those lessons learned, we're looking for themes like if they're all identifying the same gap, better robotics, more efficient batteries. It's like, okay, that's a good sign. Now, those are kind of obvious ones, but there are 1 or 2 on there I saw that were like, oh, that's actually really clever. I hadn't thought about that, and now I've forgotten. But that's why we have reports. Click, click. I don't know if that did it. So next year we have 4 tracks. We're going to cap it at 100 teams because I think that's how many mentors we have. One thing we were just batting around yesterday was the idea that like, hey, maybe we'll, even if they're not Cosmic members, allow C3 alum to be mentors if they want to do that. I don't know how that would work, but certainly if you've had the experience doing it and you want to give back, I think there's an opportunity there. Any student at a U.S. based university is eligible. Yep, this is the same thing. Midterm showcase in December, 5-minute talks, and then the final showcase probably the week of April 13th. The tracks I go through quickly. The first one is aboard a bosun's locker. That's basically the continuation of this project, except now it's really focused on manufacturing and assembly. Lunar operations, same thing, but on the moon. Track 3, this is like the San Diego State. If you guys saw what they did yesterday, that is kind of what we're proposing for track 3 is not just a payload, but a spacecraft that can host multiple payloads to do multiple things. In track 4, that's really inspired by armadas, but not limited to armadas, is what kind of megastructures can you build and how would you build them? So it's a little bit different flavor. 1 and 2 are largely the same. 2 requires a prototype. 3, we're really, if you have a large team, we're going to push you to 3. Like, and then I realized the challenge is, well, if you have a large team, but they're all mechanical engineers, track 3 might not be a good fit. So we'll take that into account and we'll figure it out. Yeah, and that's it. So with that, I'm going to turn it over to Zenith Engineering Services. This is the team, huh? Zenith Engineering Solutions, not just services. This is actually the team from University of Texas at Arlington. This is the team that I've been mentoring, so they got 100 on my scoreboard. I visited them last week at their campus, and yeah, I'm really proud of the work they've done. And come on up.
All right, thank you for that, Dr. Roan. You'll give us just a moment to get set up. Okay, let's get started. Good morning, Cosmic, C3 competitors, and anybody else involved. We are Zenith Engineering Solutions, as Dr. Roan has introduced us. We are presenting our competition and a solution towards the C3 challenge. Our advisor back at home is Dr. Paul Davidson at UTA, and our mentor is Dr. Jacob Rome here at Aerospace. Let me see if I can get this click. Oh, beautiful. All right. Trusses have historically been built on Earth and assembled in space by humans. This method of assembly is time-consuming, expensive, and limited in scope. ZES has developed an autonomous, in-space truss assembly robot that uses prefabricated truss elements to build a structure that is modular and scalable. A modular and scalable truss will enable the construction of larger spacecraft, as well as enhance the life of current space systems. A prototype of the robot was built to validate its mechanical functions and is currently progressing towards preliminary design. Here's the team. From left to right, we have Spencer, Nevin, myself, Ethan, Nicholas, and Juan. We are all undergraduate seniors in mechanical engineering, and so our project is very much geared towards mechanical engineering. Here's a timeline of everything that we've completed. To give you some preface, our senior design capstone project is structured in a way that our first semester is exclusively conceptual design. We finalized our conceptual design of the ATAR, as we are calling it, on November 21st. Starting this semester, we began to develop the entirety of the prototype, as we will see in the rest of the presentation. The impact. We chose to focus on truss building because it's a clear gap between the vision of space infrastructure and the current state of the art. Huge constructions in space could play host to many functions and support work in space, such as the future Artemis missions and putting a man on Mars. However, the difficulty and expense of manual truss construction in space means that structures are limited to what can fit within or fold out from a rocket's payload fairing. We aim to realize the vision shown here, with in-space construction yards facilitating greater scope for the future. This is the envisioned operation of our robot. Shown here is the digital twin that we've generated in CAD of the prototype, and we'll get into it further later. It can be launched into space and build a truss structure as large as needed. Once the structure is complete, the robot can return to Earth to be recovered and reused. Once the truss structure is built, it will be freed from the bus and can be utilized by whatever is in need. Shown here is the animation of our conceptual design. You'll see the torque arm assemblies grabbing each truss elements that we're calling the node and placing them into the build plane. Then the beam magazine in the center will lower down, place the beam between the two nodes, and use induction welding to fuse the thermoplastic members together. After that, the torque arm will then rotate the assembly and add another beam as needed. This can be continuously expanded as we have evacuated the build plane to build larger and larger structures, as long as you have materials to support it. Here's the conceptual design broken into its sub-assemblies. In the blue, you have the node magazines storing and dispensing the nodes themselves with a tray mechanism. Moving into the yellow structures, we have the torque arms, the most complex of the sub-assemblies. This will be lowering a torque arm into the socket hole of the nodes themselves and then affixing it with tabs on the end. This will allow the nodes to be moved and also allow locomotion of the robot on the truss structure. In the center is the beam magazine. This is what will hold and weld the beams into place. It should be noted that the entire structure has been decidedly made out of aluminum 2024, as it is commonly used in space applications for its lightweight and high strength to weight ratio, as well as reduce in fatigue. Now Spencer will start breaking down the sub-assemblies.
So this is our conceptual beam magazine as of November. Its job is to store and install the beams onto the truss assembly. It has a servo motor which rotates these pegs that you can see in the inside to isolate the beams as to have only one beam installed while keeping the remaining beams inside the magazine. It's translated using a ball screw and DC motor to move it up and down. This is a CAD model of our prototype, and instead of a servo motor, we used a dual shaft DC motor shown in red to control the pegs, and this was because the servo motors that we did have were too low power to counteract the force of the follower mechanism. Additionally, we used a rack and pinion mechanism as opposed to sliders for the pegs in the beam separator module because it's mechanically simpler for us in the prototype. We also have in orange these stabilizer brackets to prevent the magazine from twisting when the lead screw actuates. And we have a video here of the, yeah, okay, yes. We have a video of the magazine being actuated up and down with a lead screw. And for the prototype, we used a plain lead screw instead of a ball screw because the lubrication requirements are needed in atmosphere. And we also have a video of the module in action. And as we can see, as the rack moves, it allows a beam to come in the loading position, and then that motion would occur right before it's lifted up, and then another beam is ready to be placed. And I'll hand it over to Nicholas.
So, the node magazine is used to store and dispense the nodes into position for the torque arm to retrieve them. It, like the beam magazine, uses a spring-loaded follower system to push the beams down into the slot in the feeder tray, which is then actuated by a ball screw to move into the position underneath the torque arm. For our prototype, we've had to make a few adjustments due to the complexity and expense of the ball screw. We've swapped it out in this on the ground in atmosphere version for a rack and pinion system. And then the follower is pulled down by a single constant force spring at the back. And then the force is counterbalanced by bearings, 2 sets of bearings around the follower assembly, which ensure its continued horizontal position. And then there is also a cutout in the feeder tray to ensure that it can, the torque arm can easily pull the node out of the feeder. And then here we have a video of the feeder tray in action. Here the motor is going at 100% speed. It is much slower on our finalized and computer-controlled prototype.
The torque arm is the most complex subassembly in the robot. It must slot into the nodes that we use for our truss, secure the nodes, and also raise the nodes out of the feeder that slides out, slide them into the build plane, and then rotate these nodes in order to sort of in order to locomote across the truss. In the conceptual design, we use brushless DC motors, 15 watt, geared down to enable the rotation of the whole assembly. A pallet fork is paired with a servo motor, which is used to lift up the torque arm shaft you see in the picture. And the solenoid in the center actuates some flanges that actuate out of the torque arm shaft in order to fix the node to the assembly. Here's a picture of a CAD of the prototype. You can see the 3 motors that drive the torque arm, a servo in the top that actuates the flanges to secure the node, a servo in the pallet fork raises and lowers the arm, and the stepper motor connects to the gearbox and rotates the torque arm shaft. We learned that using a servo placed in the cab of the torque arm is most likely the best design choice for the final assembly. I'll pass it. Okay. So this is a video of our prototype of the flanges actuating. You go back. Not in this one. Okay. I'll pass it on to Nevin to talk about the truss element.
The beam and node shown here form our truss structure. The node, which acts as the joint, has slots at 30-degree intervals so that we can form an equilateral triangle. They're both made out of carbon fiber reinforced PEEK. And we chose this material since it is resistant to microcracks from thermal cycling, has good resistance to degradation from radiation, and it is also a common material that is used in space applications. The beams and nodes are joined together through induction welding. And the beam has metal implants, which melts the thermoplastics during the induction welding process. The method of joining is achieved using magnets in the prototype as compared to induction welding. We deem this more reasonable for prototyping, as we are just demonstrating the mechanical operation. This is a little animatic that shows the concept for how the demonstrator truss will be built from the bus. As the truss elements are joined together, the robot can rotate about one node to move into place for the next, or to effectively walk along the truss.
So, now that we've seen all the individual components, we can look at how the overall assembly fits into the requirements of the competition. The conceptual design, without the rescale and any changes made to the prototype, fits well within the payload volume of the Venus-class bus. The mass is also well within our bounds. The maximum power draw, which occurs during the induction welding operation, exceeds the maximum power supply of the single-wing bus, which we've designed our payload volume for. Therefore, we will use a supercapacitor to provide the excess supply for a momentary period in which the induction welding occurs. However, the regular power draw for all other operations does not exceed the 15 watts used in the torque arm rotation. Our analysis of the conceptual elements also shows that they can withstand the forces of launch. We have three operations we selected to combine, namely the dispensing and alignment of our nodes and beams, their joining using the induction welding, and the robot's locomotion along the truss, all of which combine towards the larger truss construction ISAM capability. Building the autonomous truss assembly robot is highly feasible due to the components used being fairly well tested and understood in terms of their history in space operations, and they're easily available. The basic operations have also been proven through the kinematics of the working parts of the working subassemblies that we've built for our prototype. And we believe that it's a simple matter of programming it for automation, which means that overall, the design in total is easily feasible within the decade.
Building the autonomous in-space truss assembly robot within the decade. Oh, hold on. Even though the mission is feasible, additional technologies could make the mission more effective. Welding of thermoplastics in space is a novel idea, and further developments in this area would improve the confidence in the mission. The ability to inspect joints, as well as reload the truss elements in the additional technologies that would amplify the impact of the mission. However, none of these technological gaps make the mission unachievable. Some of the technologies that we tested or looked at for joining were fasteners, ultrasonic welding, adhesives, snap fits, and induction welding. We were considering snap fits for the majority of the design phase, but we abandoned it due to the strength of snap fits being low and their reliability in autonomous programming being low. We ended up going with induction welding as it requires no tool contact on the weld surface. It uses EMF to heat the metal inserts inside of the beams. And this leads to a simple automation process. However, even in atmospheric conditions, induction coils require water cooling.
For linear actuators, we considered lead screws, rack and pinion mechanisms, and ball screws. The lead screw and rack and pinion were ruled out because they rely on sliding friction, which just is less effective and would would affect our reliability in our system. Instead, we selected ball screws, which is an industry standard for space applications. Mechanisms that use ball screws will be required to be sealed, which, because of the environment, it will have to use O-rings and an inert gas atmosphere for the mechanism inside of the housing to prevent bonding between surfaces and reduce off-gassing from lubricants.
Autonomous assembly of structures is not new when it comes to space missions that are under development. However, ATAR utilizes a unique assembly and locomotion operation that is significantly simpler than current assembler robots. The ATAR is also designed for on-orbit assembly as compared to building structures on celestial bodies. And it also utilizes induction welding of thermoplastics, which is a novel idea when it comes to space missions. Some of the most innovative ideas that we considered include the ability to capture and deorbit satellites that had lost communication, repairing or replacing solar panels, and induction welding of thermoplastics. The complexity of satellite commandeering as compared to its need led us to not pursue this idea forward. And when it came to solar panels, solar panel repair, there was a lack of interest on proposed solutions, which led us to not move forward with it. On the other hand, induction welding of thermoplastics is an idea that we incorporated into our mission.
All right. Risks associated with robots' operations were ranked based on severity and likelihood of occurring. Misalignments of nodes and beams ranked as the most probable and severe, since the likelihood of this is mission critical and currently lacking closed-loop feedback. The failure of different actuators ranked separately, as they all have different actions. The failure of the torque arm would be catastrophic because, in addition to mission failing, the robot cannot be recovered. Impact of space debris has no designed countermeasures, assuming the debris is large and fast, and for this reason ranks high in severity. Electronic operations are commonly interrupted due to radiation seconds in space. However, this is commonly remedied by the use of redundant systems. Regular wear and tear rank the least probable and severe, since the robot will only experience this after a long period of time, and the effects won't be detrimental to the operation itself, due to the fact that we are going to just bring it home, maintain it, similar to an airplane. Events considered in regular wear and tear include off-gassing of lubricants and material degradation in space over time. The data handling and comms is really quite simple for our robot. It does not require any real-time activation, could be constantly observed or piecewise depending on the operator, and the operator is only needed for initialization and updates if desired. This allows low bit rate. Through brief skimming of systems, we determined the AstroDev Lithium 1 to be the best choice, with 9.8 kilobits per second at 48 grams and a low power draw of 1/4 to 4 watts of power. The biggest challenges that we occurred during the first stages of development were: we realized that the assembly is interfering with the truss structure and inhibits expansion. This issue was resolved by designing the robot in such a way that all parts can be evacuated from the build plane. An additional challenge was the high power required to weld metal trusses, which was later replaced by thermoplastic truss elements. The low power specification caused some worry at first and led to the development of a robot that can operate in separate stages to prevent high power consumption. Shown here is one half of the full prototype design. On the left, you see the node magazine. In the center, the torque arm, and in the right, the beam magazine. We're currently implementing new systems or the same systems, but getting it to work, and we have another 3 weeks to make sure that this is fully operational. Our paper further details our decisions and motivations behind each thing, as well as detailing the trade studies that we performed. The abstract is 163 words and 13 pages long as the entire paper, where we reference 26 works. The path to PDR shows that we plan to design the launch configuration for the robot to fit within the bus itself, add disassembly and reloading functionality in order to increase the use of the robot, true environment testing so that we can understand the resistances that are required in order for the locomotion of the robot to not inhibit any movement of the bus and the truss structure, and to understand further the thermal loading and strategies to adjust for such. Also, we would need to rescale this prototype to fit within the bus and assign space-rated motors, as well as adding closed-loop feedback. In summary, the team started out by researching the space environment and getting familiar with ISAM. After gaining some insight into the current state of ISAM and a general idea of the space environment, the knowledge was used to select a mission that was novel, feasible, and applicable. Once a mission was selected, the design was refined through several iterations and landed on us with the conceptual design. A prototype of the conceptual design was built while making changes to facilitate this process. Shown here, you can see the initial hand sketch, kind of back of the napkin, on the first day that we thought of this idea, all the way to the final digital twin of the prototype shown above. Are there any questions?
Okay, let's open it up to the judges for questions.
Hey, I'll go first. That's okay. So this is Lieutenant Griseric. I work here in Space Force. I asked a similar question yesterday, but is there any consideration of what you'd have to change about the payload design to work in LEO versus working in GEO?
Let me repeat the question so I understand you're asking. Was there consideration of the differences in design versus working in LEO and GEO? Is that correct?
Yep.
Yes. So we found that in LEO we have a much higher temperature fluctuation as well as a radiation bombardment, although that's about the same. When it comes to the temperature fluctuation, it would fall in the same idea. Considering the aluminum 2024 is well tested and holds up well to fatigue, we did consider a different material, also aluminum 7075, but we're not sure that it would be much different. Overall, I'm not sure that the design would have to change all that much, as the truss structure itself would also hold up well against radiation bombardment, as we see very little degradation of the material. Does that answer your question?
Yeah, great answer. Great presentation too. Thank you.
Thank you so much.
Hey
Yeah,
guys,
if you-
go ahead.
Yeah, so the question I have is, you're clearly using magazines of your material. Did you guys discuss the options for, reloading those, or have you thought through any of the options to make sure that you don't get limited on orbit?
Yes, so we did consider different abilities to reload nodes as well as beams. We figured that is a very obvious path towards the next consideration, and it seems very feasible, as you can just add some sort of a gate check valve mechanism. We just didn't end up implementing it in the final conceptual design or getting CAD for it. As we work on the project further, or possibly pass it on to the next senior design team that could be working on it, that would be the very next step, as currently it only has the capacity to build small elements. We do believe that fits within the deliverables for this, as we are designing the proof of concept prototype. But yes, that is the next step. Does that answer your question?
I think we had a question online.
Yeah, hey guys, this is Greenfield from NASA Ings. I'm part of the Armadas team that you guys referenced. And one question that I had was, were you guys actually able to get the mechanisms working and put the joints together?
Yes, actually, your question is, we got the mechanisms working and joining together. We did. It was actually, we finished it Sunday evening, and we left for the plane Monday morning at 2 a.m. So we have a video. Unfortunately, we're not able to share it with you, but yes, we were able to get it functioning in the entire prototype assembled. As you saw, each individual prototype subassembly, we bolted it onto those aluminum extrusions, aligned it in such a way, and then hooked all the actuators up through different circuits and drivers and controlled it with a Raspberry Pi. We were able to get limited construction of the truss. We're going to go through further refinements, as our senior design presentation is in about a week and a half, and we'd love for it to be fully functional by then.
Nice. I really like the concept. And I guess my question was leading towards, do you guys have an idea of how to deal with tolerance stack-ups as you guys assemble the structure, or if it's even going to be an issue?
I'm sorry, did you ask about, did I hear Traveler spec ups?
Tolerance stack-up.
Tolerance stack ups. Yes, so we plan on the closed loop feedback, hoping to solve that issue, as obviously as the structure continues to expand, Nothing is perfect. We would have some sort of Hall effect sensor included with a small magnet through precision placement, but then as induction welding occurs and a swelling of the trusses start to occur, we get a little lost on the complexity. We have not yet found a foolproof solution, but it is something we had considered.
Sounds great. Thanks, guys. Great work.
Thank you so much.
No, that was the question I was going to ask about the tolerance stack up, especially because you guys identified that as your top risk. So what you're saying is your mitigation plan is to look at the Hall effect or some other closed loop. Okay, thank you.
Of course, yes.
So how do you envision moving to other planes, orthogonal planes, things like that?
That's a beautiful question. We actually discussed this with Dr. Rome and our advisor, Dr. Paul Davidson, in the beginning of the first semester. We loved the idea of volume trusses. That seems complex for what we have. We imagined some many things, some crazy ideas, like something that would bend around a pivot point. And all in all, for the scope and time that we had in this project, we weren't quite able to get it there. What we do envision for the future of this, though, is that we could possibly have multiple of these assemblies building trusses in different orientations of each other, and maybe incorporating some sort of other thing that can come in a weld or a line and join the corners, imagining something more similar to the truss construction yards that we showed. Very similar to a hive concept, having many working in tandem.
I may have missed it, but will your materials be launched from Earth and then assembled, or will they be manufactured on orbit?
They would be assembled on orbit. So we would prefabricate the truss elements on Earth, including the metal impregnation in the ends of the beams. And they would go up in some sort of depot, or depending on the number of them, with the robot itself. And then from there, assembled in orbit.
Copy. Thank you.
Of course. Thank you.
Okay, great questions. We might have time for one more quick question. Otherwise, I think we can.
So when the truss comes down into the
I have a
joint,
question.
can you hear me?
Yeah, I can hear you. Yes.
Sorry, go ahead.
When the truss structure comes into the joint, the middle joint, how you're securing in place? So you're using thermoplastic welding, is what you said?
Yes, sir. So thermoplastic welding through induction methods. So we actually considered we need to restrain it in all degrees of freedom. The axial plane, so the tension, the compression and tension of the beams is the only thing we're considering of the truss structure itself. And that is done through just the flanges that you see in the node. Now, in order to prevent it from coming out of the node itself, that is where we're using induction welding. We did this and made this decision specifically so that we do not need to worry about the strength of the weld per se, because it is not the load-bearing components of the truss. It is just to make sure the truss stays a truss. Of course, thank you.
Wait, one more question online if you want to, if it's a quick question.
Yeah, so yeah, the design looks pretty practical. I was just wondering, I can envision this constructing trusses on the lunar surface. So have you given any consideration or human factors consideration to how astronauts or anybody might go in and unjam these, or have any considerations went into the design to make them serviceable by people?
By people specifically, we had not considered that, but we do have a plan for future considerations of the project to add disassembly as well as assembly, allowing for the structures to both be modular, scalable, and deconstructible and reused. Because the only thing holding the truss together is the simple induction welds at the joints, we believe you can use an induction welder to melt it and pull the beams back out. This similar process could easily be done by humans just on the truss structure itself. So I suppose maintaining that by hand is very feasible, but it is not a consideration we had.
Okay, and went a little over
I
time,
meant like the
but-
feeder mechanism.
Go
That's
go
right.
ahead, Chris. Go ahead, Chris. You can follow up.
Oh, I meant like, for example, if the feeder mechanism gets jammed in the robot or something like that.
Oh, I see. No, that is not something we had thought of with risk mitigation. We kind of assumed that with the price of the robot being relatively cheap, they would just call it a wash. So,
Okay. All right, that's gonna have
Okay,
to do
thanks.
it. Let's thank the Mavericks again, and Zenith Engineering Solutions. And we'll just start the next talk at 9:18. Here we go. Okay, next up are the miners from the University of Texas at El Paso, presenting Patcher 1.
Hello, we are the miners and we are from the University of Texas at El Paso and we will be presenting our concept Patcher 1. So hello, starting off with our executive summary, the goal is to design a payload to be hosted about the VCT Venus class bus to demonstrate a chain of 3 or more autonomous in space ISAM capabilities. We propose Patcher 1. Patcher 1 is an on-demand antenna manufacturing system. We have chosen this because in our research we found that satellites in low Earth orbit tend to have failures, one of which we thought we could remedy was that of communications. So what we plan to do is remedy this by helping not decommission these satellites that can't communicate to finish their missions, or also extend satellites missions that could still work but need an extra upgrade. And this would also in turn reduce space debris. So hello, I'm Aida Chacon. I'm the team leader and I'll let the rest of my team introduce themselves.
Hello everyone, my name is Diego de Rio Reyes. I'm the lead animator and CAD designer for the team.
Hello everyone, I'm Jimena Morales Perez and I'm the material and technology advisor. Hello everyone, I'm Jimena Morales Perez and I'm the material and technology advisor.
Hi, I'm Joanna Arellano and I'm the lead budget and materials coordinator.
How's it going? My name is Joshua. I'm one of the CAD designers.
Hi, my name is Joel Lujan, and I'm also one of the CAD designers.
Hi, my name is Usman Olasco, and I'm also a CAD designer.
Hi, my name is Ana Martinez, and I'm the budget and material coordinator.
We would like to point out that this has been a 2-semester effort, so our team has changed quite a bit. We only have 3 of the original members, and our past members include Andres, which was our team leader, Daniel as our systems engineer, Brian was a CAD designer, Allison was our materials research advisor, and Evan was our simulations coordinator. So as a team, we have found that our impacts include that of upgrades and repairs, since we will have an space grade 3D printer, we would enable the ability to print parts needed in space, such as that of the antennas that we want. With our onboard manipulator, we would also be able to assemble the finished parts onto the satellites that we want to fix. It would also reduce resupply missions, such as having to send up a brand new satellite to complete the experiments that they thought, cutting logistical costs and challenges. Again, it would extend the mission lifespan by helping not decommission satellites that may have not been able to finish it, and just provide extra support for others.
Okay, so our system is designed to be fully autonomous in LEO, and that requires a careful balance of power. With the integration of dual solar arrays, we now have access to more consistent energy generation, which is around 6.39 kilowatts per hour per day under optimal LEO sunlight conditions. During one full patch antenna fabrication cycle, our system consumes an estimated of 1.96 kilowatts per hour, which includes printing, post-processing, sensors and monitoring, and the robotic arm operation. We have used a duty cycling strategy where high power operations like printing are scheduled during sunlight, while low power systems like sensor remain on through the orbit. Our energy model, based on the latest CAD simulations and technical requirements, confirms that the system is sustainable with room for operational flexibility thanks to onboard battery storage. Our estimated total cost is between 22,000 and 25,000, excluding future treatments or upgrades. The budget covers all major components, including the high temperature dual sturdy 3D printer, sensors and control system, thermal post-processing elements, and structural materials like PEI and copper composites. We have selected each component with space readiness, reliability, and printability in mind. For instance, the PEI substrate offers thermal stability and printability, while our conductor materials was chosen for high radio frequency performance with lower power demands. In addition, we estimate the coast antenna measuring 6.5 by 5.5 centimeters at $26.81 per unit. The dual-use robotic arm not only prints but also positions and installs the antennas, which helps reduce mass and simplify mechanical systems, optimizing power efficiency.
For innovation, I would like to demonstrate different technologies that we found that can demonstrate what we want to do. So there exists a company called WASP that integrates that 3D printing technology into the robotic arm. So we know that this is feasible. Also, we found research into 3D fully printed patch antennas. So we know also that patch antennas works. And we found a very interesting research on that proposals of Mitsubishi Electric. They propose like an antenna, they just can make one antenna out of resin in space. And there are other similar proposals is awesome too that manufactures large components. So the novelty in what we want to do is we will have the robotic arm that will be capable of grip the patch antenna and install it. To make sure we meet the required elements, as my teammate said, we selected the dual array, which we had that constraint of volume, and we created a cut model to make sure everything fit between that space. Also, we decided materials for the robotic arm, and we encountered the mass for the filaments and extra materials that we're using. And we met also the requirement. Our power requirements are confirmed by our power budget, and also the Selected spacecraft bus is capable of supporting all missions operations, being key factors such as thermal management and data transmissions. And for the launch environment, we consider mechanical loads and vibrations. And our model has three sequencing technologies, being printing, gripping, and installing.
To further prove our feasibility, we made this risk matrix. The one we saw with the highest likelihood of occurring, which had a critical impact, was that of the thermal fluctuations that we may face in LEO. This may affect our electronics, which then in turn could affect any subsystem, meaning we could have failure in the robotic arm motion or printing. The thing we want to do to mitigate this is make sure we design thermal insulation and incorporate active cooling into our payload. The other one we would like to point out has a low likelihood of occurring, but also has a high impact, is when our deorbiting mechanism could fail. So the way to mitigate this one would be just to make redundant deorbiting systems to make sure that it is very reliable. Moving on to our trade studies to help us choose what we wanted to do for this project. First off is the manufacturing selection. So in the beginning, we had just originally thought of using the simple fused filament fabrication 3D printing that we know most commonly. However, after talking with an expert that our mentor Mathis brought on, Dr. Salas, she introduced us to nanojet electrospray, which was really promising. As you can see, it actually won our trade study. However, we did meet her really late into this process. So feasibly, we went back and continued with the fused filament fabrication. After deciding on the fused filament fabrication method, we needed to concrete what antenna we wanted to make. Feasibly, we couldn't make all of these onto whatever payload we would have, but to keep things simple, we wanted to stick to one. In this case was the patch antenna, which won due to ease of printing and the use of material efficiency.
So the patch antenna has three main layers. The ground layer will be of the electric material, and then we have the substrate, and then we have the patch layer. So depending of the satellite, the area of the antenna can be modified. So a larger area will give a lower frequency, and also the thickness of the substrate will affect the bandwidth. For our substrate materials, we had PIC, PEC, and OTAM. After being the requirements for our antenna, we considered thermal stability, printability, mechanical state, and how suitable it was to space, and the best one came out to be OTAM. And for electric material, we consider copper, CNT, and graphene. For this, we consider the addition to the material of OTAM, the electric conductivity, and how printable it was, and the best one came out to be the copper.
When conducting the trade study to determine which design the claw would best suit the task at hand, we considered the following criteria. To better narrow down our choices, when selecting the design requirements, we considered what the harsh conditions in space would be like. And after weighted grading, we found that the two-finger gripper scored higher compared to the other designs. The two-finger gripper produced a higher score due to a number of factors, but one of the most important criteria that had us considered was the weight of the gripper. This is why we had to choose the two-finger claw. And the gripper is a screw-driven mechanism operated by one motor. It has two extruders at the base of the claw, and the function is to 3D print, remove the objects from the bed, and also pick up the objects and install it. It's a lightweight design. We've removed as much weight as we could while keeping it as high in strength as possible. Just note that the scrap design at the end of each head is to better pry up the patch antenna from the build plate.
Now on the following video, we'll see animation of the mission of the payload. Here you can see the payload reaching out the patch, the satellite where the patch antenna will be placed at. And after you will see how the arm will start 3D printing the patch antenna inside the payload. You can just take a while. There you go. This will see how you're gonna see inside the camera that we install inside inside our payload. After the arm finish out 3D print the patch antenna, it will start to picking it up and then taking out of the payload to place the patch antenna into the desired satellite. Now more in depth in how the mission will look like with this storyboard. First of all, we're going to locate our payload inside fairings, so for a more secure flight. Then we'll locate these fairings inside the launch vehicle. In this case, will be a rocket. We haven't decided which rocket we'll use it. Now after this rocket will launch our payload into a LEO distance. Once it deploys our payload inside the LEO distance, we're gonna make sure that communication between Earth and the payload are secure. After us, we're gonna send information for the payload. This will be the G code for the 3D print. After we finish the 3D print, it will start just taking off the patch antenna, so it can locate the patch antenna inside the satellite. Satellite. After it, we're looking for more satellites to locate the patch antenna, and after it will redeploy the patch antenna, the payload into Earth, so we can recover it and we can do more missions with it.
So even though the payload is fully autonomous, we still need real-time downlink for monitoring the 3D printing process. Sensors and cameras will help us verify that everything is working properly. We don't need an observer on board, and we don't need a full-time operator. We just need occasional ground interaction if something goes wrong. During operation, the total data rate peaks around 1 megabyte per second. And we are not designing the communication system, but we do have clear requirements. It needs to support real-time downlink, have a reliable command uplink, and be able to buffer data when there is no connection. It also has to work within our power and volume limits and handle LEO's extreme thermal and vacuum conditions. Basically, it must be efficient, autonomous, and reliable.
Using the Cosmic packet, we made a Gantt chart to help document our milestones. They're the only difference we have changed since we first made it was that when we got our new group members, we had to add some more team organization. Other than that, we've stuck to the Gantt chart as we have since last semester.
Some of the innovating concepts we had was a multi-purpose robotic arm, which we did pursue, which has an effector that grips and is able to install an antenna. One thing we didn't pursue is solar sintering. This was an idea we have later, but we think that this could make the antenna to have higher quality signals. And as we mentioned, we also found out the nanojet electrospray, which is not polymer based and will get comparative level gassing compared to the fused filament. But we also didn't pursue this concept. Some of the tech gap assessments that we have is even though we have space grid filaments, it could be a significant improvement in the required energy. Or also, as I mentioned, there are off-gassing, so it could be an improvement there. Also, the power and thermal management, we can have definitely an improvement because we are having really high temperatures and also in situ antenna performance validation in space.
So for this concept, the biggest challenge was the concept itself. Initially, we did not know what to choose for the first few months. We first thought of making a recycler robot that would get scraps from space to make whole new satellites. The other one, we were heavily inspired by OSAM 2, which was building superstructures, but we did not know what to do with those superstructures. So as a team, we couldn't really latch onto this idea. Eventually, with talking with our mentor, we discovered we did really like the idea of manufacturing. So we geared towards the idea of printing antennas for a more specified use. After we came up with this idea, it was really hard to make it actually innovative. So what we originally thought was just getting a 3D printer and a robotic arm, both separate systems, and they would work in conjunction. However, we then figured we could combine them both and have the robot both 3D print by opening the claws and also being able to be the manipulator itself to install them later. The other challenge was balancing the energy demands. Originally, we were using the single array, bus. That was not working out for us with the temperature that we needed to reach for the materials. So we opted for smaller space, but which was fine. We were able to consolidate most of what we had and have the dual array system with 444 watts. Here's our path to PDR. We made a diagram. As you can see, it starts really wide at the top and narrows down to a more concrete concept. Essentially outlining everything we've done up to now. In the beginning, we made a very initial CAD of the actual volume. We started thinking of how the data communication would flow. Started with the systems engineering for the risk assessment and safety strategies. After that, we had to move on to the system requirements because our ideas were still too broad, so we needed to keep the constraints in mind, which helped us a lot, such as the power, volume, and mass. We considered how autonomous it would be and the command levels we needed, as well as starting to get the environmental factors that we needed for this to be able to happen in space. In the preliminary design, we did the CAD models for the payload so we could start with the animation for the ISAM operations. And we conducted our trade studies, as you saw, to get the best components and help us with our planning. The safety strategies and mitigations, as you saw. And the concept of operations is where we planned out better how it would go through these process, as well as the ISAM operations that we want to demonstrate for Cosmic, and how our payload would be fitting onto the Venus class bus. Finally, we're here where we prepared the PDR, the preliminary design review. We would plan on the testing methods for such our payload and our timeline and milestones as by the Cosmic guidelines. So in conclusion, we propose Patcher 1, a on-demand 3D printing antenna payload to install antennas onto other satellites in orbit. This robotic arm would be in situ for satellite upgrades or repairs, since it also extends the life, minimizing orbital debris, enabling for modular, scalable, and resilient space operation. Questions?
Okay, we have plenty of time for questions, so judges, feel free.
Hi, really appreciated the idea. I love that you picked the patch antennas. I haven't seen anybody look at this in particular, so I was glad to see the team do that. I'm curious, of your risks, what's the number one thing you might want to try to test on the ground before you go into like from PDR to CDR? What's your biggest concern for manufacturing?
I would say the actual signals that the antennas can produce. We did see the paper of the research that we provided there of a fully 3D printed patch antenna, although we didn't fully look into how that communication signal that they were able to generate, how it could help communicate satellites between. So it would be more like how that antenna would be able to generate the signal to make it actually useful to upgrade the satellite.
So performance validation of the antenna to your print. Thank you.
You have a composite antenna which has a copper plate basically with the polymer surround, I suppose. I don't have the right terms. Is the copper, is that correct? First of all, just head nod, yes or no? Yes.
Yes, it's correct.
Okay, so is the copper plate fabricated on orbit as well, or does it come from Earth? And do you, if that's the case, well, answer that first.
Yeah, so we have two nozzles. So yeah, the two materials are in our payload.
Okay, and you have to build the copper on orbit?
No, we found a copper that is a filament. So we found the copper that is already a filament and is used already in this type of printing fused filament.
Sorry, that's what I meant. So you'll use 3D printing to create the copper plate.
Oh, yeah.
Okay, and then how has anyone done this where they had to deal with the different thermal properties and the adhesion and issues like that for an antenna?
Yeah, we found one article when one antenna was fully 3D printing of metal, and we found other one that was fully 3D printing of antenna, even though we didn't find one that combined both. But that's why we are implementing also the build plate. But
What
we do have problems handling these high temperatures.
what kind of issues would you foresee in having this combined polymer copper fabrication process?
One being of gassing, and then Ultim does work to the addition to copper. So I don't see a problem combining both.
Okay, thank you.
Thank you.
Okay, do we have any other questions? Okay, before you leave stage, I forgot the first team, but can we get a photo of them on stage together? And then Mav, Zenith Solutions, you guys as well afterwards. And I'll just say, I think it's really cool. So far, we've seen ideas for replacing or restoring batteries. We've seen it for repairing solar panels, adding a patch antenna. I think we're going to see some stabilization like gyro replacement tomorrow. You know, like we talk so much like servicing, and everyone's refuel. And I think you and many of the other teams have kind of identified, hey, there's a lot more we can do to satellites to keep them servicing, to repair them, than just put in more fuel. So I think that's really cool. So I'm going to stop talking. Oh, okay. We're going to change the lens, so I'm going to keep talking. No, I'm just kidding.
What you can do is you can turn in this way and each side, like face each other, like if she's on the left. That way.
Great job.
So after this, these students are going to go over to D8 for a tour of the MRL and the Cave Lab, and then we will resume here, I believe, at 11 o'clock. start just 5 minutes and then we'll get started. The teams haven't returned from the tour yet. But if they don't return in 5 minutes, we're just going to go ahead. So just please hold for 5 minutes. Thank you. Okay, we are back live here. Next up, we have Equinox from Penn State University talking about the regolith refinery. You guys go ahead.
Perfect. Thank you very much. We're very excited to be here today. Good afternoon, everybody. Good morning, still technically, I guess, if you're on the West Coast. My name is Zachary Gall, and I am honored to be representing Team Equinox here from the Pennsylvania State University. Today, we're going to tell you a little bit about, or give you an overview of our Equinox regolith refinery that we've been working on for these last 2 semesters here. So we'll go ahead and get started here. So the overall problem that we are facing here is that all spacecraft must be manufactured on Earth and then sent up to space. This is not only expensive, but it's very inefficient and it's not sustainable. So what we proposed is that why don't we manufacture 3D printer filament from in-space materials? This provides construction material from space that can be used in space and eliminate that reliability of our, determination, our need for Earth's resources. Now, how does this work? Well, it is going to require mining and some printing of spacecraft to be fully usable. What we came up with is 3 main operations. We have crushing of that regolith simulant, sorting of those particles by size, and then mixing those particles into a filament paste. So currently we have a good conceptual design and a functional CAD model with an animation to share with you guys here today. So next slide here. Before we get down into the details, just want to reiterate, just myself, my name is Zachary Gall, but we also on our team, we had Fedi Borky, Sean Marino, Peter Bachman, Blake Monska, Srisharan Srinivasan, and Devin Thomas. So next slide. We started our project back here in August of 2026, our first day of fall semester in 2024. And that whole semester, what we did was basic introductory research on ISAM. What is that in-space, assembly and manufacturing? And what area of that ISAM did our particular team want to focus on? So once we did our trade studies, chose our particular area of focus, we then defined our system requirements, the objectives that we wanted our payload to accomplish, and then went ahead and did final trade studies to get down to a good conceptual design idea. Moving into that spring semester, we broke down our system into smaller subsystems, conducted trade studies on those, and then came up with our final conceptual design that we're sharing with you here today. Next slide. So our initial brainstorming concepts that we came up with here, we wanted to use the full diversity of our team. So what we did, we kind of broke our teams up into 3 separate little teams, and we came up with 3 early innovative concepts. And these kind of used a variety of different technologies. We had things from harnessing the force due to centrifugal acceleration. We had things such as chemical mixing and the chemical properties of that, all the way up to suspending our regolith in a fluid and utilizing a pump to move that throughout our payload here. So by utilizing all these different technologies here, we were able to come up with all these different innovative concepts centered around utilizing that microgravity environment. Next slide. So after we had these 3 concepts, we came up with a bunch of different assessment criteria. We weighted these assessment criteria based off of how important we felt they were to achieving our overall mission goals, of providing that uniform and widely, ability to use that construction material in space. What we came up with was concept 3, as shown on the last slide, was our highest weighted sum based off of this assessment criteria. So we went ahead and we utilized that concept going forward, and then also drew the best parts of those first 2 concepts as well, and meshed all of this together into the conceptual design that we now have as the Equinox regolith refinery. So, looking at our overall mission architecture to start, We are utilizing the SpaceX Falcon 9 rideshare program. We have our first phase as launch, and then we will arrive on orbit. Once we're on orbit and we have, our payload exactly where we needs to do in that, Venus X-class bus, exactly where we need it to be, all we have to do is send up a single activation signal, one uplink to activate that payload. That internal payload is going to carry out all of those actions, and we will cover those actions in a separate architecture here as well. And then once it's done with that, we will send a verification signal back down to our ground station in Alice Springs, Australia is our ground station location that we chose for this. And once we have that final signal down, that final verification, we go ahead and we decay our orbit. Next slide. So here we have a animation of our CAD, kind of showing you exactly how our payload is going to operate. So for the sake of this demonstration, we simply wanted to show that the processing of this regolith material in a microgravity environment while in orbit around a celestial body is possible. So the best and easiest way that we found to do this was to bring a simulant, a lunar regolith simulant, based off of, the composition of what lunar regolith is based off of research, bring that with us in an initial storage container and process that. So after it leaves that initial storage, we bring that regolith down through a roll crusher. That takes that regolith down into uniform particle sizes that make it easier to then sort that out inside of our centrifugal sieve, which is our next step there. After that material is sorted by its density there through that centrifugal sieve, we then take that down into our mixing chamber, combine it with our binding agent, and then that then goes down to our final storage. Now, all of this material is being moved through our payload using a compressor and a pump. We suspended our regolith material in a nitrogen gas. So that is the fluid helping us move this through here in our microgravity environment. And we are also utilizing hydrogen that we can use as a binding agent to have that fluidization to cause that solid material to become more like a fluid. Next slide. Also here we have a payload rendering. This helps us, show that our payload with all of its components here in its structure that we just showed with the animation fits inside of that Venus X-class bus and meets those constraints that we originally had here. So next slide. We also went ahead and we did some structural and thermal verification. This is one of the biggest, benefits of having that detailed functional CAD model is that it gave us, good interpretation based off of our thermal distribution and how the finite element analysis was going to look for this particular payload. We decided that we needed to wrap our payload in a silver Teflon, and that gave a cold case exterior temperature of minus 77 degrees Celsius. Because we were experiencing temperatures all the way from minus 77 up to 47 degrees Celsius as well internally. So the heat generated by those onboard electronics is going to be the main cause for bringing that payload up to that local maximum, that 47.85 degrees Celsius that we mentioned. So further looking into the structural analysis side of this, we realized that we needed to have a carbon fiber reinforced polymer payload, and that payload that we used there, that was just going to deform on its own based off of our launch loads that we that this payload was going to undergo launching without Falcon 9. So the aluminum bus structure maintains a safety factor of 1.4 under those Falcon 9 launch loads, which is roughly 5,000 newtons. So with that rigid connection between those two, we can go ahead and ensure that structural integrity. So we found all of these different structural and thermal verifications based off of, these different studies that we did here as well. So moving on into the material processing form of this, as I mentioned earlier, we are using a BP1 regolith simulant, and that's going to allow us to, simulate, not have to actually dock with a structure or another spacecraft. In order to get that regolith, we're going to bring it up for this shear demonstration that it can be done. We already talked about that crushing mechanism for the uniform particle size, the centrifugal sieve, and then down through the mixer. We also wanted to focus that we are going to be using metrology And that's going to be using, that's going to be a benefit for allowing us to measure that final product and ensure that our mission was a success there. How are we going to do that? So we wanted to look into spectroscopy, and spectroscopy has the ability to give us that final composition of that material so we can verify exactly what competition and what molecules, what compounds are in that final storage chamber, and we can do that through our spectroscopy. But just having the composition wasn't enough. We kind of also want to know what the consistency of that and, you know, and the workability and how that material is going to be able to be utilized. So by adding a humidity sensor as well, that helps us verify that consistency and the moisture content of that final product. Those were our big metrology aspects adding on here as well. Next slide. We did various trade studies, and all these trade studies were for our individual subsystems. We had all of the basic subsystems that would fall under a normal, you know, NASA systems engineering, basic, you know, small satellite space system or subsystems, correction. But we also had our unique ones with the crusher, the sorter, and the mixer as well. So just our basic trade study on our crusher here showed that our roll wheel crusher was the best fit for us. So that is why we chose that based off of our data shown here. And then moving on, we also did a trade study with our sorter, and based off of these metrics that we found, your GNC, the normalized adjusted TRL, power draw, things like that, we chose that the centrifugal sieve gave us the highest, you know, weighted total for that as well. So that was what we went with that trade study. Our structures trade study showed us that thing that we talked about, the idea that we talked about earlier based off the carbon fiber reinforced polymer versus that aluminum 6061 T6. So based off of this trade study, we found out that we are going to do that rigid mountedness. We need that aluminum as well because we don't want that carbon fiber polymer to, you know, crush under those loads and the benefits of each one of those. We found that out during this trade study. The compressor trade study, it gave us a lot of different information, and this one was especially useful because we had to kind of adjust what compressor we were using. The main thing we had to focus on here wasn't our total weight. Our main things that we needed to focus on were size. So you can notice that the Celeritron, the 15150, was significantly smaller than the other two compressors that were shown, and it had the lowest amount of maximum power. So those were the two biggest takeaways for us here and what we found out with this trade study. Our internal communications flowchart, moving into our data handling in the comms. It's a very simple overarching mission architecture here and a very simple overarching external communications. But our internal communications is a little bit more detailed here, and it's sequential. So once we get that command execution received, we're going to go ahead and verify all of our prerequisites, make sure that we're not, you know, firing off our process until we are exactly ready to do so. Once that happens, we activate our compressor. That allows us to move that regolith, that suspended regolith around. Once that compressor is activated, we go ahead, we do our crusher, and then we do our centrifugal sieve, then we do our mixer, and then we go ahead and extrude that to our final storage, and then we do our final verification. It's a very sequential order here, and we'll talk a little bit about that with our risk analysis, but this was the easiest method to do that we chose, just also based off of power requirements. So because of the power draw of each one of these individual systems, it was most beneficial for us to have intermediate verification steps along the way and process this material sequentially. We have a mass budget here as well, and I just wanted to point out that the main things are the bulk majority of where our mass is going is for those payload specific subsystems. So that crushing, that sorting, and those are typically, you know, they need to be stronger components, and those stronger components tend to weigh more. They have more mass. So you can see right there, just crushing alone is 35% of our total mass as well. We added a margin of 10% there. Our total payload mass we had at 70. We used a payload to bus ratio of 1.5 that gave us our bus mass of 105 for all the subsystems that are required in that Venus X class bus, which gave us a total mass of our payload and our X class at 175 kilograms, and that would be our total launch weight. Looking at our power budget as well, very similar in terms of subsystems and the draws for those as we have with the mass. You can see that just focusing on our payload for crushing, sorting, and mixing, those are our largest power draws. And it makes sense because crushing, you think of anything, a large industrial type, equipment, it's going to take a lot of power in order to shape that material into something that's going to be usable. So it was no surprise for us there, realizing that those payload-specific subsystems are our main form of power draw here and what we had to focus on. So breaking all of that down and looking at total cost. So the aluminum, the carbon fiber reinforced polymer, they're relatively cheap, but the command and data handling, all of the electronics with that, and all of the internal, since it is all mostly internal, that was our largest expense. So at roughly $56,000 there for, after we priced out all those components individually, rough estimates of those, and combine that all together, that was almost 50%. It was 49% of our total budget there, but it brought our payload bill of materials to a cost of $113,300, and that does include a 10% margin as well. Now, circling back and looking at our overarching communications architecture, I wanted to focus on this because it highlights our autonomous, our semi-autonomous and in future work, fully autonomous capabilities of our spacecraft. So we did a link budget to conduct the precise values of exactly what our uplink's going to look like, exactly what our downlink's going to look like. And all we have to do is send up that initial command signal, that execution signal from our ground station. Once that's received, we do our internal processing, and then we get our final verification, and we send that back down. Now, if there's, failure codes throughout there, our mission is set up to do multiple orbits. And so therefore, if we don't get a good verification or prerequisites are not met on our first window of communication with our ground station, we do have multiple opportunities to go ahead and execute that internal processing on future orbits. So we added that in as well as a added redundancy there. We're using a space wire system for our internal communications. We do have that redundancy with non-volatile memory. That way we can store that telemetry data and all those payload parameters on board until we are finally ready to send those down. So that way we don't need a constant communication link the entire time, and it gives us a little bit more flexibility as well. So further looking more into, essentially the details of that communication. So I mentioned it's a semi-autonomous capability. We have one uplink and we have one downlink. That uplink's roughly 72 bits. We can call it 100 bits with our margin, and our downlink is 150 bits as well. We are going to be utilizing the ground station in Alice Springs, Australia. It works very well from us launching from Cape Canaveral on a Falcon 9, being able to utilize that as we just launch straight into our orbit. We don't have to worry about incline changes, different maneuvers. Once we're finally launched, we are able to launch directly into our orbit and have sufficient coverage using that Alice Springs, Australia ground station. So I mentioned our risks a little bit earlier here, but I also wanted to show, our map here as well. So what are our biggest risks that I wanted to highlight here? That sequential operation is our biggest one. A failure in one step is going to cause an entire mission failure. But how do we counteract that? We have sensors at every single one of our steps, and we can have manual overrides as well based off of, as I mentioned earlier, if we do have like an error code coming through in one of those intermediate steps, we were able to send that error code back down when we would normally send a verification signal down. We can send that error code back down. Based off of the parameters, we know exactly where we're at in our process. We know exactly based off of the parameters, do we meet the prerequisites to move on to the next section? Is there something we can do? Is there a way that we can maneuver our spacecraft? Is there a way that we can move things around in order to allow us to continue this mission on as well? So that helped us mitigate that risk and allow us to go ahead and continue moving on with that sequential operation. Also coupled with that sequential operation is that power draw. So because each one of these systems draws, so much power, we really needed to do that sequential operation in order to have enough power with our dual solar array and those 444 watts. So that way we could ensure that we had, the correct amount of power draw for those high level power draw payload specific subsystems that we talked about earlier. We also saw that flow choking or, clogging of some of those pipes could also be an issue here as well. So material buildup that could, definitely cause us some flow issues. So, but also sensors at the end of each one of our pipes, checking that differential pressure across some of that, that allows us to kind of look like, can we recycle this fluid? Can we, maneuver our spacecraft a certain way, just how we would, look at those other sequential operations and troubleshoot that as well. So these were all of our different mitigations, and that allowed us to not have anything that was, very likely severe, likely significant, things like that. So we feel like we did a very good job mitigating our risks here moving forward. What would benefit our particular, payload moving forward? Well, definitely asteroid mining or different surface mining spacecraft. That would definitely, help boost the need and the advancements in this particular area of ISAM. Having those spacecraft be able to mine the material for us and deliver that material to our refinery would be a huge impact to our specific technology. Also, advancements in our 3D printing. So since we decided to make a 3D printing filament, we found that having that 3D printing capability allows you to essentially build anything you can dream of based off of the limitations on your specific 3D printer. So increasing and not having limited factors on those 3D printing machines would allow our payload to have an even greater impact. And then also just, servicing our payload as well, the ability to inspect and perform maintenance on those would, advance the lifespan of ours as well. We encountered I already mentioned some of the challenges that we encountered here. We are in microgravity, so we needed to move materials with non-traditional methods. That's why we are suspending and using the compressor. We have high power draws, so we need to focus exactly on what time we're activating these payloads. And then also implementing this with the Venus X-class bus. It was, almost like a blank canvas with a few, constraints on us, but based off of our internal processing of our payload, it allowed us to be, very unique with those integrations. We do have our technical paper submitted. Our abstract length is 188 words, 20 pages, and we utilized over 20 references, and we would potentially publish it in the AIAA SciTech. Integrating this with the bus, we mentioned a little bit earlier, we are rigidly mounting it. We allowed 94 watts of power to go towards our bus, and our dimensions do fit with inside that payload, and we are within that 70 kilogram limit. Future work, we already kind of talked about. The ability to dock with other spacecraft to deliver that regolith would be super helpful. If we were able to scale the spacecraft up to higher, bigger dimensions, that would greatly improve the ability or the amount of material we're able to process. And then moving this, away from ground activation signals would give us a full autonomy ability as well. And it's very, simple to implement that. So in conclusion here, just wanted to highlight our key capabilities are crushing that regolith simulant, sizing that simulant down, and mixing it into a 3D filament paste. We have a good conceptual design here. We have a working CAD model, and we think this is super important to ISAM and our, our future as humanity and being able to, move off of planet Earth and have, a future in space amongst the cosmos. And with that, open up for questions.
Okay, perfect timing. And judges, if you have any questions, go ahead.
Hey, it's John Vickers. Can you hear me?
Yes, sir. Yes, I can.
Hey, Zachary, John Vickers from NASA. That's an excellent presentation. I might not have heard it earlier, but I heard at the end that you had considered the effects of microgravity. And as I was listening, I was thinking about that. Can you explain just a little bit more about where you thought microgravity might cause you some problems?
Yes, sir. So the biggest thing that we figured out with microgravity is if you look at different, pump systems on Earth, a lot of those pump systems, all these pumps, they require pump head, some sort of pressure upstream of that pump in order for that pump to operate properly. So we counteracted this with this microgravity. We figured that, we would need a physical, mechanical, ability to push this through if we didn't utilize the properties of like a fluid. So by utilizing the properties of our fluid and suspending our regolith inside of that fluid, we are able to compress that fluid down and pressurize it. And by having a 30 psi absolute or 15 psi gauge pressure inside of our system on launch, we then have that pump head, that pressure that would be required in order to allow these pumps to operate here. And so we looked at different types of pump. You have the basic centrifugal pumps moving that fluid through, but you also have those positive displacement pumps as well. So the biggest challenges with that microgravity was just being able to move that material when you don't necessarily have a traditional, say, a large tank of water providing pump head to the inlet of your pump to assist with that flow. If that answers kind of your question here.
Yeah, that's it. Thank you very much. Great
Thank you,
presentation.
sir. Thank you, sir.
Yeah, from aerospace, maybe a follow-up question to that. I wasn't following. Do you have gates between the different stages of the processing so that you only put regolith into one stage at a time?
Correct. Yes. Yes, and that might not have been fully clear on our CAD design, but the idea of it would be that regolith stays within that specific subsystem. So once we verify based off of those sensors that all that regolith has been crushed properly, then we would allow that, gate, for example, to open to move on to our centrifugal sieve. And then once that's verified, we allow that gate to open, move on to our mixing. We allow that binding agent to come in and move it on. So yes, it is a very, structured, separated, and separate verification procedures before moving on to that next subsystem stage is our main focus of that sequential as well.
Okay, do we have any other questions from the judges? Okay, we are right on time, so let's thank our speakers once again.
Thank you, everybody, for watching. I appreciate it. Looking forward to the rest of our presentations here. Thank you very much.
Okay, next one is up in 2 minutes.
Could I actually present the slides from my device?
Yeah, that's fine if you need to do that. Okay, you guys can go ahead. Next up is Iowa State University, the Space Cyclones.
Good morning. My name is Jonathan Bueter. I'm here with the Iowa State University C3 Capstone Challenge problem, the Iowa State Space Cyclones. Join with me today, I have my teammates Riley, Daniel, Ben, Mahika, and Tanvi, who you'll all hear from separately. And today we're going to be walking through our design. So our overview, the problem that we're looking to solve with this device that we've created is addressing the issue of debris in low Earth orbit. Currently in low Earth orbit, there's estimates of thousands of pieces of debris on multiple size scales. And with our device, we're trying to create something that can address this problem. So our solution, the Space Cyclone, will deploy net capsules from our Venus bus payload to be able to target and deorbit pieces of debris. Our satellite itself uses multiple reloadable NAT capsules to deorbit several pieces of debris with one single operation. And at the time of this presentation, we have prototyped and 3D printed our net launching module, as well as our net launching capsule itself, and designed microcontroller logic and code to target and deorbit pieces of debris with our system. So approaching this problem, what's unique about our group is we're doing it through Iowa State University Senior Design course, part of the Electrical Engineering and Computer Engineering department. And so with that, we have certain different course deadlines that we had to adhere to, as well as C3 deadlines. So in September, we went through the process of forming the group, creating a program manager, and kind of going through the process of designing how we were going to even start to solve this problem, given the fact that we have varying backgrounds that are not aerospace related. So moving through October and September, we really started to understand and develop project requirements. Moving into November, we defined the system requirements, how we were able to approach this problem, and different ways that we could solve kind of the broad scope of ISAM. In January, we decided to hone down on the idea of deorbiting pieces of debris. February, we worked with our industry partners and advisors to be able to create that preliminary design review. And at this current state, we've created our prototype, microcontroller logic, and are currently working on the code to actually create that prototype to be able to fire a net capsule at a simulated piece of debris. With our design, we're looking to deorbit pieces of debris anywhere from the range of 10 centimeters to 1 meter in size. By doing this, we'll be able to reduce debris collisions within space, creating safer future operating environments for other payloads, and promoting sustainability within space. Our design is allowed to operate within a sustained development period. We will be able to restock our net capsules after we've depleted them with future operations, and our payload itself will be able to continually last and hopefully continue to clear debris from lower Earth orbit. With our design, we really took inspiration from the removed debris prototype that was sent up in 2018. With this prototype, it was able to demonstrate that net capsule capture is possible within the space environment. And with our net capsule design itself, we're trying to maximize the payload space that we have available on the Venus bus. So given our size and weight restraints, we're able to fit about 4 of our net launching capsules into the Venus bus payload and be able to deorbit, ideally, 4 pieces of debris. Our spring launch system that we're using to propel our net capsules out of our craft will be able to reduce the amount of potential offset of forces that we'll be able to generate from our craft itself, allowing for less fuel to be used to maneuver the craft in a position to be able to deorbit more pieces of debris. And with that, I'm going to pass it over to Mahika to talk about some of the innovations of our design.
All right, thank you, John. I'm Mahika. And there's some form of echo. I'm going to wait. Sorry about that. Thank you, John. I'm Mahika, and I will be going over some of the innovation in our solution. So our goal is to provide an autonomous multi-target capability that is also a reusable platform, something that hasn't been done before. So given, like John mentioned, given the current space and weight constraints, our solution offers up to 4 to 5 net capsules, and thus those many deorbits. Our satellite has the ability to also be reloaded after exhaust and be launched again, which saves a lot in cost. We also want to really limit our ground communications as much as possible. And so we're limiting it to just being the confirming of a launch after a target has been identified. We also aim to provide a precise net capture and deorbit through an onboard LiDAR array that is able to see incoming debris and predict a certain time and location of this debris through an onboard primary microcontroller. So this primary microcontroller then communicates with the secondary microcontroller on board the net capsule that then maneuvers to the debris and deorbits. Thus, the precision is kept of high priority in order to prevent any failure. So moving on to the next slide, which is the required elements, which I don't think it's clicking. Okay, thank you, John. We are providing an autonomous service in space with our three main operations, being the launch of the net capsule, to then the capture of the target, to finally the deorbit of the target. So it is also important to recognize that our solution is predicted to be able to be implemented by the end of the decade. And this is due to the fact that a lot of the material and component has already been thoroughly researched and space tested. The process itself of a net launch and capture has been successfully tested in 2018. And our solution improves on that through an autonomous and multi-target net launch capability. If we move on to the next slide, we'll see that our solution also meets all the size, weight, and power constraints of the Venus bus design challenge, as can be seen. And for considerations of operating in space, the initial net capsule launch will be soft launched in order to reduce any Newton's third law reaction forces. And the capsule will then pilot itself to the space debris. With this solution, we also avoid the problem of tumbling in space, or at least reduce it, whether it be the tumbling of the host or the debris, since we do not provide a tethered solution. Our proposed solution is also cost-effective, with the highest estimate being around $15,000 for the payload alone. The reason that we have such a vast difference between our highest and lowest estimate is through sacrificing some of the quality of some of our components, such as the LiDAR array. We aim to use the state-of-the-art products as much as possible, which do end up costing more. So if we move on to the next slide there, we can talk about some of the risks that our team has taken into consideration. With our main objective being to deorbit cube satellites and debris from low Earth orbit, we must also have the ability to avoid other debris that may hit our platform. We must also avoid failure as much as possible, since we don't want to add on to that Kessler syndrome. And so we want to reduce that probability to zero. With fueling in mind and the fact that fuel costs a lot and we have very limited amount on board our platform, we must also plan to deorbit with whatever fuel we have. And with that, I'll pass it on to Daniel, who will be going over to the path to PDR.
So as part of the path to PDR, we have two different main types of testing that we want to do. We want to do functionality testing and feasibility testing. Functionality testing more is a proof of concept that we can do the things that we're saying we want to be able to do. These are motion, traction, and prediction of the target object, the projectile guidance of our Cyclone capsule, and the reload and refueling procedures required for reuse. For feasibility, this is about operating within our environment. This is in regards to launch testing of the design. How do we get it to space? This is vibration testing and heat testing. Vibration testing being done with vibration table, and heat testing being done primarily by looking at what has been used in the past and how they have fared, as well as zero gravity testing of the design, which we are working on prototyping in a two-dimensional environment, so a flat surface or frictionless surface, but in addition to that, additional testing via parabolic flights or drop testing. Some of the things that we looked at when designing this are, as stated earlier, we went with a untethered net design. Part of the steps to that was we initially looked at using a robot arm, but because that would allow us to have fine control. However, the biggest con with that was we were extremely worried about it breaking due to the mass and inertia difference when actually connecting to our target object. And we determined that we weren't capable of designing around that with our limited knowledge space. In addition to the tethered design, the tether would allow it to be completely reusable, but the entanglement and potential loss of the main craft would draw us away from that. We additionally looked at other methods of propulsion than gas, specifically ionic propulsion. However, while this would be more energy efficient, we determined that this would likely be too slow for our soft launch, as by the time our capsule reached the target, it'd be outside of our operating range. Therefore, we went with gas propulsion, which is more common in use and despite its limited fuel. Now I'm going to pass it off to Ben, who's going to talk about our animations.
So first we'll look at an animation of our soft launch mechanism. There's two main moving components within this. So the first on the left is the piston that moves and compresses a spring to then generate the force needed to push the capsule from the container out into free space. To create this motion, there would be a servo motor and cable attached to the plunger. This is just not shown in the animation. And then the other spring is the reloading mechanism, which there's two capsules shown in this container that are being fed into the launching space. And then once the piston moves, it'll launch them into free space. So next we'll go ahead and look at what happens after it's been launched. So in this animation, all of these components would be attached to the net. The net is just not shown in this animation. So the parts that are expanding are the 6 sides, which create the net compartment in the front of the capsule. So what happens is as those expand, those will pull the net apart and then cause the net to expand to entangle the target object. So to generate this expansion force, there are cold gas thrusters in the rear portion of the capsule. So that's that solid piece that's not expanding. And as the capsule moves, say left to right on the screen, along the axis of travel, those cold gas thrusters will generate a rotational motion. And then that rotational motion will create a centrifugal force, which will cause those net capsule sides to then open up and expand the net. So with that, I'll turn it over to Riley to begin our storyboard.
Thank you, Ben. Good afternoon, everybody. Like Ben said, my name is Riley, and I will be sharing the story of the operation of our solution. So our solution will start out, obviously, in the Venus bus and will be transported to low Earth orbit by a launch platform that's suitable for the Venus bus. Once in low Earth orbit, it will be sent instructions from a ground crew that has identified a piece of debris for deorbiting, and it will travel to this debris. Once in operable range, it will deploy a net capsule that will autonomously target the debris that we've selected for deorbit and capture it with a net and push it into knock it out of low Earth orbit so that it can burn up in the atmosphere. Some sustainable operation considerations. Our payload is configured to support resupply of net capsules and gas propulsion. Continuous resupply will allow our craft to operate as long as there are no technical failures on board. Alternatively, our craft will be able to deorbit itself if that becomes necessary. This next picture here just depicts a nice Saturn V rocket with our Venus bus on board. This is the Venus bus once it's in low Earth orbit. Also depicted here is a piece of debris that is going to be targeted. And then you can see from back on Earth, we have some information being sent to the Venus bus as far as where this debris is located. Here's a picture showing a net capsule being deployed, and as it moves toward the targeted debris, a net expands, which eventually will capture the debris and knock it out of low Earth orbit, where it can burn up and will no longer be a harm to any other satellites that occupy low Earth orbit. With that, I will pass it over to Daniel again.
So part of the data handling and communications aspect, as stated earlier, we want to restrict ground communication to a minimum to remain as autonomous as possible. As Mahika stated earlier, this boils down to only really communicating the assignment of a target and updating its status. This will include the size, mass, location, and velocity of an object in order to perform a sanity check to autonomously determine the feasibility of actually capturing this target, and also making sure that it doesn't conflict with any execution times of other planned missions. As stated, we will have a fully autonomous mission operation with our built-in observer, which will be capable of tracking and predicting the target's motion, launching and guiding our Cyclone capsule to capture the target, and directing the capture target to its accelerated deorbit. Now I will pass it off to Tanvi.
Thank you, Daniel. I will be talking more in depth about the more innovative concepts that we as a team developed through through November. The first one was manufacturing metals in space using 3D printing. Our design aimed to capture the debris in space and melt them down melt the metal down into components for different services. The second one was a satellite tug, a fuel station in space. The second one was a satellite tug, a fuel station in space, which aimed to serve as a tow station or a gas station, which would be used to refuel satellites, position them correctly, and maybe and 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 in turn as well deploy new ones. The core idea was mobility and in-space serviceability. However, we face major limitations due to size and fuel constraints imposed by the Venus bus. Last, anti-satellite weapon shielding of spacecrafts, which was developed with the idea of increasing concerns over anti-satellite weaponry. Our concept was a Kevlar shield around a satellite that could act as a bodyguard, absorbing potential blasts to protect more valuable space assets. The aim was to offer protection as a service, especially in volatile orbital zones. Moving on to the most technology gaps identified, low-cost lightweight LiDAR and camera arrays. While high-performing LiDAR systems exist, they are often too large and power-intensive for small satellite missions. Smaller alternatives suffer from accuracy and reliability issues in space conditions. Our design uses a LiDAR, and due to the weight constraints, we had to settle one which was lightweight. This demonstrates the need for a small space-hardened system to handle duties like autonomous navigation. Moving on to adaptive thruster control, conventional thrusters lack adaptability and autocorrection for misfires. An adaptive system that can self-correct would significantly enhance safety and precision. Autonomous or on-orbit inspection and repair. Manual inspection methods dominate. No autonomous repair systems are available currently, and they require Earth-based control or astronauts' help. Fully autonomous systems capable of diagnostics, minor repair, and status reporting could drastically extend mission lifetimes and reduce costs. The biggest challenges that our team has faced, main challenge that our team faced was limited aerospace background. All of us do not come from an aerospace engineering major, so it was very difficult for us to research propulsion, thermodynamics, and space materials. We also faced constraints with weight and power. Tight budgets required careful component selections and trade-off to balance performance. Our LiDAR was a prime example for this. We also face challenges with design complexity, especially in integrating different subsystems like mobility and sensing. Balancing modularity, reusability, and reliability in such a compact platform was not trivial and required multiple iterations. The last was thermal management, which posed a serious problem. Space presents extreme temperature shifts, and we lacked extensive design experience. We relied on passive thermal techniques and had to carefully select materials that could endure harsh environments without the need of active cooling. I'll pass it on to Ben for explanation of the prototype.
All right, so now looking at our physical prototype, as John mentioned at the very beginning, we had other requirements as this project was offered through our Capstone course. So we had to make a physical prototype anyway. So what we did is we've simplified down to a 2D space and focused on the mechanical side and the electrical side. So on the mechanical side, the two images on the left, we have a 3D printed scaled down model of our soft launch mechanism. So for scale, it's about the size of a Nerf gun. So that's what the orange component is, and then like a 3D printed Nerf dart representing our capsules. And then we have the disassembled and assembled spring launcher mechanism. And then on the right, we have our electrical system. So on the top of the image of the right, we have our LiDAR system, which is then used for detection and tracking of the target objects. That is then connected to the Arduino microcontroller on the bottom left, which we'll use to predict the motion of the target object, which for simplification, we've gone with just a linear motion. And then that will then control the servo motor, which is on the right, that blue box, which will then control the mechanical aspect of the prototype. So wrapping up, again, the main objective of our design is to capture and deorbit space debris using the space cyclone net capsules. One of the biggest challenges and what reasons that directed us towards a net was objects tumbling within space. So using the net can reduce or effectively eliminate this factor. Another thing we learned about were the effects of recoil, which then influenced us to create a soft launch mechanism, as is done with many other space projects. We also learned a lot about just like having space constraints, so like your mass velocity, working in orbits, and just being in that kind of an environment. So the next steps going forward for this project would be to construct a full-scale prototype, test in microgravity or zero gravity space environment, and then we would switch from our linear mechanics model, moving to an orbital mechanics model, as would be seen like in the actual use of this design. And finally, we would revise the design to support net capsule reloading based on our ConOps. So thank you so much for your time. And with that, I'd like to open it up to questions.
Okay, let's see if we have questions from the audience, from the judges.
Chet, can you hear me?
Yes, we can hear you.
Okay, thank you. So you mentioned something, I think, about some terminal guidance for your projectile. Did I hear that correctly? And if so, how would you propose to do that? How do you plan to aim, I suppose, the projectile at the target?
So the goal is we have, sorry about that. Oh. Hopefully I'm not echoing anymore. Okay, yeah. So the goal is that our net capsule has thrusters towards the end of the capsule. And so the entire net capsule is an array of thrusters, and we also have a secondary microcontroller on board. And so the goal is the primary microcontroller, as can be depicted in these pictures, will really assess or predict the location of that incoming debris and provide that information to the microcontroller on board the net capsule. So that net capsule will then guide the thrusters. So we have about 4 cold thrusters on board. It'll guide that thruster and make it go toward that particular debris. Does that answer the question?
Yes, you're describing a very complex problem, and I appreciate that this is a simple design and in early stage, but you're on track for how you might actually do that. So good.
Thank you.
I have a question, and it's just, like you mentioned, you're gonna shoot the net basically at the debris, and that's gonna help it burn up in the atmosphere. But have you considered how much velocity you need to give to the net in order to bring down an object of different sizes?
So I'll take that question. So part of that is in our determination of feasibility using the size and mass of the object, as well as its initial predicted path. If the object is too far, we will take more of our fuel to get our capsule to the target. And we're basically making an estimation of how much fuel we have when we reach the target. And as a result of however much fuel we have as that predicted amount, we have an estimation for how much we can change that velocity. And based on how much of a delta we can apply to that velocity, we determine if it's feasible or worthwhile to actually commit to said mission. Does that answer the question at all?
Kind of, but specifically like once you've reached the object, my understanding was you shoot the net at the object, and then like the net and the object would then go into would burn up the atmosphere because you knock it out of low Earth orbit. So I'm asking, like, have you thought about how much velocity you would need on your net in order to slow the object enough that it would actually get caught by the atmosphere?
We don't have a specific number.
Okay. I understand too. You guys mechanical engineers, so it's it's not an easy one. But I mean, the thing is, the bigger the object, the faster you have to shoot the net, or the bigger the net has to be. So it's definitely a design consideration in the trade space. Is there'll be limitations on how much that goes. You guys are electrical engineers, so and yeah, so that's good. I appreciate the answer, and I really liked your concept overall. Thank you. And any more questions?
Hey, Jacob, Jeff from Aerospace. I'll ask an electrical engineering question, and especially since you did some prototyping. I'm curious, you guys talked a little bit about your budget and trying to pick quality components. Given what you've prototyped and what you learned, where would you invest your money most in getting to PDR? What's the biggest developmental risk you want to try to burn down?
I can take that question. I think a lot of our research really went into the LiDAR array, and we found some very unique or interesting LiDAR arrays that are now state of the art, which is that it is also integrated into a camera. So our main goal main goal is to avoid errors as much as possible. And so the greater our LiDAR camera is, the better our precision model. And therefore, I think as an electrical engineer, I think I would put my money mostly on that LiDAR array there. Everything else is just a cold gas thruster. It's a net. These are all very set components that have no scope for really improving. And so I guess, does that answer your question?
Yes, thank you very much.
Thank you.
Okay. Well, let's thank the Space Cyclones once again.
Thank you so much for having us.
And our next team will be up in 2 minutes.
Alrighty, good afternoon, everyone. We are the Space Bender team from Cal State LA, and this is our Cosmic Capstone final briefing. Our advisors were Michael Thorburn, and our mentors were Horace Lee and Antonella Pinola. Slide. So our agenda for today, we're going to be introducing the team. We're going to show an animation of our system animation. We're going to be covering our subsystems, our environmental design, some tech gaps, our path to PDR, and finally our conclusion. So the team consists of Brandon Peffer, myself, Zeke Blanco, Raul Gutierrez, Nicholas Adams, and Oscar Rodriguez. So humanity has a problem. Anytime we try and launch things into space, we're typically limited by the volume that we can fit inside the fairing of a rocket. This is expensive, time-consuming, and limits the boom designs that we can send into space. Our solution that we're proposing should act as a stepping stone for an ecosystem of ISAM-capable technologies to create to bend wire into the form of truss blocks in space. How it solves the problem. This provides on-site fabrication requiring fewer launches, having a shorter timeline, and thus unlimits our truss sizes to any size, any shape, and any length. The current state of this project is a completed conceptual design.
This is our milestone timeline. Starting in late August, we initially started this project and quickly selected our team manager, Nicholas. We then decided on what operations we would have for our ISAM, and that snowballed into defining those system requirements. And once we reviewed them over, we did trade studies and came up with our final conceptual design.
Okay, so the capability of this technology is to bend wire to form truss blocks in orbit. So what that means is, in order to do that, we'll have spools of wire up to 400 feet, which are loaded into the payload. And by a series of operations, 1, drawing the wire, 2, twisting or rotating the wire, 3, bending the wire, and 4, cutting the wire, we are able to make these truss panels or truss blocks. In addition, we have subsystems which are split into for each operation. So we have the feed, pull, rotator, twist, bender, bend, and cutter, cut. So as mentioned before, we can make blocks, 3D and 2D shapes. And I just want to start off with the impact. So this technology is critical for the ISAM community for a couple of reasons. One, it enables or is the first step to creating modular booms. So that's important because now you can get booms, and let's say you want to make it longer, you can add a couple more blocks to it to increase its length. You can also make it wider. You could choose besides making it longer. And in the situation where a boom gets damaged, instead of replacing or scrapping the whole thing, you can simply replace the block that was damaged. Additionally, this is important for Aerospace Corp, NASA, and the Space Force because this can be integrated into planned ISAM ISAM environments. An example of this would be the small sat roadmap factory, which is planned in the next 10 years to create small sats. This can be integrated into its roadmap by creating the primary and secondary structures in addition to other manufacturing processes such as fused filament fabrication to make satellite structures.
Here we have a brief animation of our operating processes. If we could please have the video play. First, the extender in the feed mechanism extends the bending head. The rotator then ensures that the proper angle is achieved before the bender successfully completes a bend. This process is repeated until the desired shape of our final truss is gained. The entire system, when it is in its compact form, has a length of 26.5 inches and a width and height of 11 inches, as well as only weighing 58 kilograms when loaded with a spool, far under the 70 kilogram limit we were provided with our bus.
Next is our storyboard of operations.
Next slide.
Next slide. It begins with the launching of the payload and the satellite aboard the Falcon 9 rocket. Once in orbit, the satellite deploys and extends the payload, and the spool is then loaded using other operations. Sorry. And the bender and the bending head begins the space manufacturing and fabrication and releases trusses of blocks. The cycle continues with when the spool is reloaded after 6 years, for about 6 years. After the mission is complete, the payload and the satellite is deorbited. Sorry. Next, please. In order to determine the best way to feed our wire through the system, we had to first determine the type of rollers we needed to use. We did a trace study on 3 different type of rollers, and we determined that motor-driven rollers were the best choice due to their low capacity, durability, and low maintenance needs. Next. This on the right, you can see our feeder. It uses 4 motor-driven rollers to feed the wire through the system. On the left, you can see our feed flow chart, which outlines its properties.
So here's a trade of the rotator mechanism. So as a reminder, what it does is it twists or spins the wire actually. So we looked at a couple of mechanisms. We looked at a spool or mechanisms that turn the spool. We looked at mechanisms that turn the wire itself instead of the spool. And the different requirements that we looked at is, one, can it hold the spool while it's spinning? Does it have good precision and torque? And finally, the mass and volume footprint. Ultimately, we decided to opt with the spool arm and gear. So that is turning the spool externally. So while it has a higher mass and volume footprint, it provides the best torque and it holds the spool. And here is a picture of the actual mechanism. So as you can see, there's an arm which holds the spool in place, and that's connected to a gear which rotates and is powered by a motor. On the left-hand side, we have a process flowchart of the rotation.
In order to successfully complete the process, we needed to decide what type of bending we were going to use. We looked at the speed, how complex the actual bending device was, the complexity of parts it could fabricate, as well as the range of angles it could bend, how many dies it has, and its final size. With all of these in mind, we decided to go with rotary draw bending due to exceeding in a majority of these fields, and in the fields where it did not exceed, it was only marginally worse than its competitors. Slide. Here we see a similar flow chart to the previous 2 systems, showing the process in which we complete a bend. On the bottom, we can see the full bending head with its extender fully extended, showing the full length that the wire would need to go. The bending head can rotate both clockwise and counterclockwise, ensuring it is very versatile in its usage and its ability to complete bends in 2 directions. Thank you.
After the final product has been finished and the wire is ready to be cut, we need to decide on what is the best cutting method. We had mechanical cutters, the ECM, the electrochemical machining, and the grinder. We had to judge it on the criteria, most importantly, the debris that is created when the cut is made, the speed at which it makes the cut, the size it takes inside the actual ISAM device, and the power it will consume, and the material compatibility for its versatility with other projects. As we can see, the mechanical cutter did get a higher score. The ECM did have the most important aspect, which was the debris collection. However, it would be much too big to fit. It would definitely surpass our volume restrictions. It drew too much power, and it was very slow. So we went with a mechanical cutter. Ours is specifically a guillotine style. Next slide. This is what it looks like. You can see the wire passing through it. It's very simple. It will receive the instructions to cut. It will then begin checking for the presence of the wire. It will adjust for the proper cut, make one last check for position just in case for an error, and then start the cut. Next slide.
So the material that our blocks to be made out of is something to be decided. We evaluated promising alloys against desirable material properties. For example, we wanted strength, bendability, stress, corrosion resistance, and the fact that it required no prior work. When these materials were evaluated, it was deemed that 316 stainless was the best choice due to its high bendability, its resistance to corrosion, and the fact that it has no need for prior work before being able to be worked with. Next slide.
So traditional trusses are composed of different members that are connected at nodes. Our design would scrap that and instead have a continuous piece of wire act as all those together. So there would be open nodes, and a pitfall to this is that they would have to be joined since they're open. But onto the actual products that you can make with this. As mentioned before, you could stack a bunch of cubes together. You can make different 3D shapes such as pyramids. You can make panels, different 2D objects. And this is particularly interesting or important for a small sat factory because it can be scaled up, and depending on what the user wants, you can make more complicated shapes than what is seen right now. Here is the design for low Earth orbit. So for our moving parts, we opted for mechanisms that are self-contained in some housing, which is titanium. The mechanisms themselves are made out of tool steel, and it is lubricated with molybdenum disulfide, a space-grade lube. Additionally, all mechanisms are ran by 2 motors for redundancy, so it can operate to its 6-year lifespan. And outgassing is avoided by design due to the materials.
We go back one slide. Our bender will be protected by its housing made of titanium, very thick, and the outer shell will be protected with multi-layer insulation or a thermal blanket. The spool itself will have its own shielding mechanism that will fold out, and the insides will be protected by thermal pylons to regulate the heat, and phase change material to store and also help with regulation. Next slide. The multi-layer insulation will come in the layers of aluminum Capstone, Dacron mesh, beta cloth, and tape, also known as polyamide-based adhesive, that will be used to edge everything out and provide a little bit more stability. These materials were chosen based on their resistance to atomic oxygen, their ability to deflect radiation, and very low thermal conductivity. Next slide.
So seen here is a control block diagram, which shows the flow of signal or commands from the user controller to the motors, and the feedback loops are made. So the signals from the sensors, which are brought back to the controller to make sure that the motors are precisely positioned.
Here we have our data control block. On the right, you can see our mechanical sensors. Those combined with the cutter sensors give us a % completion of the product during its fabrication. This would then be sent down to the controller on the device before being sent to ground control, where it can be delivered to the client to ensure that there is proper completion of their order. In addition to this, we also would be taking temperature readings of the device itself, the wire as it is being bent, and the bending head as it is far from the main body and will require its own temperature readings. This is to ensure the safety of the system and ensure that it functions properly during its entire lifetime.
So to design for launch and a prosperous life of the mission lifespan, we have a series of tests that we split up into 3 categories, specifically mechanical tests, thermal tests, and functional tests. These were labeled either a 1 or a 2, and things like strength can be accomplished by analysis to ensure that this works for the lifetime and launch. Other tests like sinusoidal, random vibration, thermal vacuum, and failure-free performance with end-to-end compatibility is to ensure that our technology exists and functions for its entire 6-year lifespan.
So here's a chart showing the technological readiness of different components in our system. The subsystem, we have a range of TLR ratings. So our bender and cutter mechanisms are at a 4, meaning that the tech has been validated in the lab. Our feeder, rotator, and motors are at a 6, which means the tech has been demonstrated in a relevant environment. And our attitude control and data handling is at an 8, which means the system is complete and qualified. Overall, our system readiness is at a 2, which means we're still at the technological concept level.
Here we have our risk assessment chart with the impact should these errors occur on the x-axis and the probability of these errors occurring on the y. Slide. In our low risk range, we have wear and tear, positioning, and cut errors. In order to avoid regular wear and tear, we have managed to design the device so that the materials are strong enough so that they should not be an issue during the operational lifetime of it. As for positioning and cut errors, we have systems in place for reattempting these to ensure that an accurate angle and cut is performed each time. As for a bending error, the reason why this goes up to a moderate risk is due to it changing the physical properties of the material due to strain hardening. While we have similar processes for reattempting bending, if that cannot be completed or if it would cause danger to the device, the structure would be removed and the process would then be reattempted from the beginning. Material contamination would be the material just not being up to our desired standards, including things such as surface contaminations, or perhaps if they were made poorly and are not fully homogeneous. In order to avoid this, we would be doing predominantly quality control testing, ensuring that the material is of a proper quality before it is installed onto the device. As for our high risk, we have exceeding power requirements and truss impact. In order to avoid exceeding power requirements, we're actually keeping our power usage below half the supplied power of our satellite in the double solar panel configuration. And as for a truss impact, that would be the structure we are constructing coming into contact with the satellite or the payload. In order to avoid this, we have our extender, which extends the truss far out from the main body, ensuring that it cannot come into contact with the system as it is being fabricated.
This is our fall recovery plan. It is designed to protect the satellite by detecting any anomalies within the subsystems. If an anomaly occurs, the system will shut down and ensuring the safety of the satellite. Next. These are our 3 most innovative concepts. The first one was the use of the stainless of a pre-notched tube, which bends at precise points to make structures. We didn't go with this plan because we couldn't find a way to load the material into the bender, and also we had concerns with the structural integrity of the notches. And that allowed us to think about a solution, which was the use of a stainless steel spool, and that allowed us to have continuous feeding in one load. Our third concept is our bending system itself, because it's a compact system that allows us to bend in space and build structures.
The biggest challenges during our project was initially we thought too big. We wanted to have robotic manipulators to help assist in the bending process. However, when we went through the idea, it surpassed our volume restrictions, our power requirements, and the heating would be such a huge problem that we can't multitask that much. So we pivoted away. We had considered friction stir welding to be added in this process to add structural integrity to the builds. However, again, the power restraint came up again, and heating was also going to be a problem. So we pivoted away once again. We then settled on a bender. We started considering more on the volume, and that's when we had to reiterate and modify that design, and that's where we have now. Next slide.
Here we have our path to PDR, the work that is left to be done, should this project be taken up. First things first, cost analysis and budget. We claim that this is supposed to be something that is more affordable than current processes, so a verified cost analysis is very important. We also would need a development, testing, evaluation, and lifecycle sustainment plan, and for all of these to be peer reviewed to ensure that they're at the proper quality. We also need very specific software, as while CNC software for similar machines does exist, they do not function or have the requirements for the same environment that we are doing it in. While robust attitude control systems also exist, hence our 8 on our technology readiness level, they have not been implemented on this design specifically and thus would need to be researched to be used properly. And then lastly, as we have talked about many times, the joint securement method, ensuring that these have the proper strength required by securing each of the joints where a bend has taken place.
So to wrap things up, this technology is critical to the ISM community for a couple of reasons. The first is that it enables modular booms. So if you want to expand it, you can expand it. If it needed to be repaired, you just replace the part. If you want to make it longer, wider, you can do that. Additionally, it doesn't just stop at booms. You can make any shape you want up to a point, which opens the door for more complex structures. Additionally, the payload itself is a small footprint, mass and volume-wise. Lastly, this technology can be integrated to planned ISM ecosystems, such as the small sat factory, and can complement key manufacturing technologies such as fuse filament fabrication to fab these small sat structures. We will now open the floor to questions.
Okay, do our judges have questions?
I really like your simple, it's innovative and simple. That's why I like it. Question I have for you. Have you thought about how will you join the locations where you have, no connections? Have you put some thought about the various approaches that you may go about it?
So we have looked into a few different methods for joining the joints. As we mentioned in our challenge section, we looked at friction stir welding to join these joints. However, it exceeded the power requirements and the heat production requirements for our specific satellite. We also looked into securing the system with something like zip ties, but again, we just didn't have the excess power with keeping the power consumption low on our device. With this in mind, we decided it would be better to have a secondary satellite that would finish the construction and fabrication on these blocks once they have been bent into place to ensure that they have their stability.
Yeah, I'd like to add to that. So ideally, you would want a non-permanent fastening method or joining method. So one idea was to use the material used for, you guys know, slap bracelets. Like when you go to an event, you slap the bracelet on your wrist and it it gets slapped, right? So that's a type of bistable steel. We were thinking about using that. And so instead of slapping that steel onto your wrist, it gets slapped onto the 2 wires of the truss box, which hold them non-permanently.
Hey guys, this is Greenfield from NASA Ames. I have a quick question. Why, I'm just wondering how you guys came up with the block geometry versus different types of geometries, other geometries.
So the reason why we chose the blocks is more of as an example for the capabilities of this. The device could be uploaded with a variety of different patterns and instructions to fabricate other shapes. However, based on the research we did, we found that blocks were a good, versatile example to show the capabilities of our device and something that could actually be used in the space environment.
Got it. Thank you.
Jeff from Aerospace. I thought you guys did a really good job on the fault protection logic. That was, equivalent to what we see in the professional world. And I'm curious, you also had specs for the control tolerances on the mechanisms, the angles. How are you planning to measure that and use that to control the structure and alignment of the truss as you build it? Can you explain?
Yeah, so we were thinking about using some. Oh, I don't need a mic. Okay. Possibly just absolute like measuring device, so like a rotary encoder, something to measure it while it's in the wire. Yeah, we looked at rotary encoders, and we just settled with that for now.
Your specs were based on equipment that you can find,
Yeah.
what specifications they have, not alignments you would need to actually build a 3D structure. Is that correct?
They were commercials, yeah.
Yeah, so
Yeah.
based on commercial spec sheets. Thank you.
Do you guys have any idea about how like the manufacturing tolerances between different types of blocks from this process?
Could you rephrase the question, please?
How repeatable do you guys think the manufacturing process for blocks can be from the bending process?
So with the sensors we have in place, we should be able to form accurately bent blocks with fairly accurate repeatability. We have pretty tight tolerances because we know that in space, a 1% difference can mean the difference between landing on the moon and missing it by 100 miles. So we wanted to ensure that it could be done accurately, which because of this, we actually sacrificed the speed of which we can produce. While there are other bending processes that are faster while being just as accurate, they take up more space and more power and aren't necessarily as versatile when it comes to the production process. So we wanted to have something that had a good mix of reliability in the angles of that it could bend, as well as speed and versatility. And that's why we came to rotary draw bending. So we should be able to fabricate these blocks accurately with repeatably over the course of the lifespan and with multiple spool reloads.
Cool. Thanks, guys. Great work.
Okay, any more questions from the judges? Okay, I'd like us to thank our Space Bender team. You guys have a wonderfully simple concept and did a great job, as all the teams have the past 2 days. That is gonna, well, first let's hear it for the team. So this ends the West Coast portion of the first C3 final showcase. Tomorrow it will pick up on the East Coast. I'm not flying out there, but you know, and there'll be I think 6 out of the 9 teams tomorrow will be presenting there in person as well. So you know, it's been great to meet so many students. It's been great to see these projects and kind of like what we wanted to get out of this was we wanted to get a lot out of it, but we really like to hear the echoes over and over again. You know, like different ways of making trusses or building truss elements or different kinds of services and repairs you can do, right? What are the like 2 teams in a row yesterday had gecko material, right? Some of the technology gaps identified are common and things that aren't necessarily in the top of the list. And it's been really good to kind of see them all at once. It's a little bit of a fire hose if you've been hanging out, but it's very educational and very inspiring. So thank you to all the teams that participated, and I'm really looking forward to the final day tomorrow and seeing 9 more great ideas. Thank you. You guys can stay for a photo, and like whoever can stop the recording. Thank you.